In this problem, the only real difference from the last problem is that we've now got three forces acting rather than two forces as we had previously. But all the methods remain the same. So again, these forces are not all acting on the same point. But as we mentioned before, there's no reason why you can't trace these points or find the line of action of this point. So basically you just trace that force back. You can do the same with the other two. And trace them back. And then you could just move all of these forces into that point where they all join together. So you can move this force back to here, move this force back, move them all back. And basically you'll get the forces all acting on the same point. It doesn't have to be like that, but for the moment, the problems I'll give you will be like that. All the forces will join up and act on the same point. And so what I've done next is just draw that to scale. So that's all those forces drawn, acting on the same point, and I've drawn those to scale using my ruler. Just going to move it down a bit. And then the basics of adding any vector, doesn't matter what it is, force vector, displacement vector, is that you're placing them nose to tail. And so the essence of what we're doing is we're taking this force, we're putting it nose to tail here. Then we're taking this force, putting it nose to tail up here. And your resultant vector is just going to be the vector that joins the start point to the finish point. Like so. So as usual, we could skip all the trigonometry if we didn't want to be too accurate. We could just draw a scale drawing and figure it out that way. Now this is 900 newtons. Let's see how many divisions we've got. 5, 10, 15, 20, 25, 30, 35, 40, 45. So I am doing 100 newtons for every 5 divisions. 100, let me just check that. 100, 200, 300, 400, 500, 600, 700, 800, 900. So let's see what we've got for a resultant. We've got approximately 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 1400. So maybe 1420 maybe. I better put that in green because it's just an approximation. And the angle is around 55 degrees. So it's about 55 degrees. So we've got about 1455 degrees. I'm going to move this out of the way in a minute. Oh no, that's okay, I'll just leave it like that. So that's cool. Okay, but we don't really want to draw it like that. So let's put that back. Because it looks like the point of action of each of those forces has changed. And so what we do instead, and again, just to save time, I've done that already. So let me just drag that across. So I've sketched this out already. Sorry for jumping around a little bit. So we're imagining taking this vector, put it nose to tail, that's it, ends up over here. Then we take this vector, put it nose to tail, it ends up here. And you could have done those in the other order. You could have put this one across first and then taken the 600 Newton force across and put it on top of that. But it doesn't really matter, you get the same answer. So then we're looking at that and we're thinking, okay, so now we've got the vectors laid out nose to tail. So originally it would have just have been these, this one up here, this one up here, this one up here. Then you're looking for your x and y components of each of those. And so I'm going to I've looked for some triangles. So there's one triangle there, right angle triangle, another one here. So I've just numbered them 1, 2, 3. So I've got 3 right angle triangles that'll let me get the x and y components of each of these forces or the force vectors. So then we need to try and find the angles in those. So for this first one here, we've got this 900 newtons. we know that the angle between horizontal and that's 30 degrees, so we know that this angle here is 30 degrees, sorted. Then we look at the 601, we've got to be careful, it's 45 degrees to this vector, so the total angle in there is the sum of those, so 45 plus 30, so we've got 75 degrees in there. And then this last one here, we've got the angle from horizontal to the 200 Newton force is 41 degrees, so that's what I've got here. So now I've got my triangles with my x and y components of each of those forces. If we add those all up, so we add all the y's together, and then we add all the x's together, we're going to get the y and x component of the resultant. Then we'll end up using Pythagoras to figure out the value of that. So what we'll do is I'll work through that. I'll speed up the video a bit, and then I'll meet you on the other side. Okay, so where we've got to here is we've calculated all the x and y components. So the next thing to do is just to combine those together to get the x and y components of that resultant. So I'll just do that now. Now I'll just say a few words here. What you'll have noticed is I had a look at that and then had a look at my result to check it just against the scale, and I noticed it didn't look right. So then went back and had a look if I'd got my directions correct, and I noticed that I'd forgotten that this x direction is heading in the negative x direction, so it's heading backwards. So I've gone back and fixed that and made these negative, and then I'm going to recalculate that answer. And then we'll look at combining those back together to get the resultant. So back in a minute. Okay, so I've checked those two answers, they look reasonable. So now we find the x and y components, we found the x component and the y component of this resultant force. So we just do a quick sketch, just so that you can follow along. What was the angle? Well, we don't know yet. And so we're looking at this resultant, and I'm not even going to do this to scale, we've got the scale drawn above, and we found the x and y components of that by adding up all the x and y components of the individual forces. So we now know that this is 803.8 newtons, and this is 1185 newtons. And now we've got two sides of a right angled triangle. We want the other side, so we can use Pythagoras to get the magnitude of F, and then we can use tan to get that angle. So now I've calculated the magnitude and direction of F, and I've checked it against the sketch. So my sketch is getting a little bit inaccurate because you're adding lots of different vectors, and I was a bit sloppy about how I drew it, but they're looking approximately correct. So then we just write out our answer. And so resultant force has a magnitude of 1431 newtons at 55.8 degrees above horizontal. And just to cover my bases, to the right. Okay, so that's that one. So same as usual, so let's just go back through it quickly. So we just took the force, we imagined putting those nose to tail, found all the x and y components of those vectors that we're adding up, added those to get the x and y component of the resultant. I'll just put a direction on that. And then use Pythagoras just to get the resultant and tan to get the angle there. We'll just underline our answer and we're done.